Hi guys! This morning CERN officially announced their results, showing that they found a new particle which has the correct properties to be a Higgs boson. In this video I'll try to explain how they came to this result. First of all, the search for new particles is done in particle accelerators. The quest for the Higgs is done at CERN, using the Large Hadron Collider. There are 4 experiments on this collider, 2 of which are used to find the Higgs boson, namely the Atlas experiment and the CMS experiment. A key property of particle accelerators is that we know what we put in and what we get out, but not what happens in between. It is like a black box. Note that new particles not necessarily appear in the end state of a collision, because in general they are unstable and will decay to other particles that are already known. Then how can we discover a new particle if it only appears inside the black box? For this we use the theory and statistics. The theory described in the Higgs boson predicts different production modes for the Higgs and different decay modes for the Higgs. All of them are exactly calculable and are the key to give an accurate description of what can possibly happen in our black box. In practice, the experiments only see the end products, since their input is fixed to 2 protons. So it makes sense to group the data analysis to the different decay modes, also known as channels. Different people in an experiment will work on different channels, and only in the end results of all channels get combined. Let me elaborate a bit on one channel as an example. The decay where the Higgs goes to 2 photons. Since we cannot see the difference between the different production modes, because they occur inside the black box, we have to sum up over different production modes. Then we get diagrams like this one, where each proton sends out a gluon, going in a quark triangle to a Higgs, decaying via a quark triangle to 2 photons. If we now calculate the energy spectrum and count the number of collisions at a given energy, theory predicts that we see a bump in the number of collisions around the place where the energy equals the Higgs mass. But now comes the tricky part. Let me remind you that we cannot make a distinction between all possible interactions that collide 2 protons producing 2 photons, because in reality we are working with a black box machine. But there are lots of different setups that go from 2 protons to 2 photons. The easiest example is the same diagram as before, but the Higgs simply gets replaced by gluon. If you then calculate the energy spectrum of all these non-Higgs setups, we get a huge amount of collisions, much more than those with Higgs in it. This is what it's called the background, as it is everything we will measure which is not a Higgs signal. The total energy spectrum is then this huge background plus a small bump around the Higgs mass. Actually, this picture is already overestimated, the bump is even smaller. So then, how do we handle this? With statistics. Everything can be reduced to chance. In this case, the chance of having a collision resulting in 2 photons with an intermediate Higgs boson is much smaller than the chance of having a collision from the background. But that doesn't mean we cannot quantify it. You can compare it to flipping a coin. When flipping a coin, we expect to get a 50-50 chance division between head and tail. However, whenever I do only 2 flips, I can easily get, for example, 2 times tail. This is not 50-50 at all. But when I do 10 flips in a row, the result will be already better. The more flips I do, the more the result will approach a perfect 50-50 distribution. This is the main idea of statistics. The more data, the better I describe the underlying theory. So in our case, only 5 collisions is not enough to separate the Higgs signal from the background. Then it is more likely that the collision didn't have a Higgs in it. We need several orders more collisions to be able to clearly make the distinction between bump or no bump. In other words, Higgs or no Higgs. It's all in the data, and preferably as much as possible. So, what does the data show us? CMS presented its analysis of all data taken in 2011 and 2012. Their combined result from all decay channels shows us they discovered a new boson with a mass of 125.4 giga-electron-volts within 4.9 sigma confidence level. The other experiment looking for the Higgs at CERN, the Atlas experiment, confirms the CMS result by finding a new boson with mass 126.5 giga-electron volt within 5.0 sigma confidence level. The final result will be a combination of the two with a mass somewhere in between and an even higher confidence level. What do we mean with this 5 sigma? It is a criterion that tells us how reliable a result is. It gets calculated from statistics. Simply said, the more data you have, the higher your sigma can be. Whenever we have a result with 3 sigma confidence level, it means we are 99.73% sure the result is correct. This is then officially called an observation. Whenever we have a result with 5 sigma confidence level, it means we are 99.99994% sure the result is correct. This is officially called a discovery. In the end, did CERN discover the Higgs boson? The answer is maybe, or most probably. What we know for sure is that CERN discovered a new particle, not yet seen before, that has spin 0, but technically it can still be a spin 2 non-elementary particle, but okay, that has its mass somewhere around 125 and 126 gigaelectronvolt, and that only interacts with particles that have mass. What is not yet sure is that it's exactly the Higgs boson, in other words, that it is responsible for giving that mass. And by the way, if it will be proven to be the Higgs boson, it can be the standard Higgs boson, meaning only one type, or one or more types of supersymmetric Higgs bosons, or even more exotic things. There is still lots to explore in the elementary particle universe. Thanks for watching.